You're listening to the Good Question Podcast with Richard Jacobs. Our goal is to make each of our guests exclaim, that's a good question. I don't know the answer. Because when that happens, it means you, the listener, may be inspired to learn more beyond the interview and to ask great questions yourself that lead to new insights. In this podcast, we cover historical and current anthropology, comparative religion, and history. Welcome, and let's get started.
Hello, this is Richard Jacobs, the Good Question Podcast. I've got an excellent guest, Dr. Andrew Snelling. He's a geologist and author of Earth's Catastrophic Past, Geology, Creation, and the Flood. I saw him on a YouTube video series called Is Genesis History? Listened to a bunch of his lectures on radiocarbon dating and some of the geological work he's doing, talking about the dynamics of Noah's flood, etc. So I think it's going to be a really great call. Welcome, Andrew, and thank you for coming.
Glad to be with you, Richard.
Yeah, if you would, tell me a bit about your background. How did you, get into geology, and were you always a person of faith, or did that come as you were a geologist, came later on?
Well, I was born and raised in Sydney, Australia. You can tell from my accent. And I was raised in a Christian home and regularly went to church. But when I was 8 years of age, I went on a vacation camp, and that camp, I made my own decision to be a Christian. And saw the changes that resulted. A year later, the family, we went on a vacation from Sydney down to the southern state of Tasmania, off the coast, southeastern tip of Australia. And we visited a mining area. And I got to see all the shiny rocks and crystals, and I started to collect them. And I was in the fourth grade of school. You know what it's like in show and tell. As soon as you start knowing more about something than all your peers, you get more and more interested. So by the time I got to high school, I was passionate about geology and was convinced I was going to become a geologist. But of course, I had to struggle with these issues because, I had the Bible teaching at church, and yet it seemed to conflict with the textbooks that I was looking at and learning from. And so it was in my teenage years that my mother got a copy for me of the book, The Genesis Flood by Drs. Whitcomb and Morris. And it was the result of reading that book and weighing up the geological evidence that I became convinced of the issues that we're discussing this afternoon.
When you started out, were you a young Earth creationist, or did you have a view that things are millions and billions of years old?
Well, the church that I went to had grew up with a Schofield Bible and put the gap, the meres in the gap. And I quickly realized that was untenable. And so I moved to being a young Earth creationist. So by the time I got to university, I was thoroughly convinced as a young Earth creationist.
Okay. And a lot of your lectures talk about radiocarbon dating. When did that become an important part of your research?
Well, it was actually during the 1990s. I began work in full-time creation ministry with Ken Ham back 40 years ago, almost, the end of 1983 in Australia. And as a consequence, I started looking at the issues, and radiocarbon would come up. And so I thought about it. And in the 1990s, when I was on various field trips or speaking engagements and traveling around, I decided to collect some samples of fossilized wood and send them off for radiocarbon dating without telling the labs where the samples came from. And so, for example, I had a fossil tree stumps from coal beds north of Sydney, Newcastle area, famous for its coal mines, and it's supposed to be Permian, 250 million years old, and yet it had radiocarbon in it. It was only thousands of years worth of radiocarbon. I found fossil wood from a milestone in England that was supposed to be 189 million years old based on the index fossils in it, and it also had radiocarbon in it. So I had done a number of these sorts of studies in the mid-90s before I got involved in the Radioisotopes and Age of the Earth project, RATE project, the acronym for it, that was started by the Institute for Creation Research in 1997. And it was in that project that I encouraged Dr. John Baumgartner, who was looking for some experimental work to do, because I was involved in other areas of experimental work in the RATE project. But I supported John Baumgartner in doing some radiocarbon work during the rate project.
Okay. What were some of the issues that you started to see in regards to, radiocarbon dating and other dating methods? It seems like there's a huge gap. We have C14, which I believe the half-life is like for 5,700 years. And then there's a uranium isotope that's like billions of years, but there seems to be an enormous gap. There seems to be nothing that's been, let's say, 50,000 or 100,000 years for this half-life. So what are some of the dynamics of the problems you've seen with dating methods?
Well, all the methods are based on assumptions. There are a few methods that are sort of bridge the gap a little bit into hundreds of thousands of years. They often use things like thermoluminescence or optically stimulated luminescence, but they all have their assumptions. It's based on exposure of the rocks to the sunlight, and that affects some of the minerals like quartz, and then they get buried and they lose some of that effect from the sunlight. And so you can compare surface to depth, but there's always assumptions that the rate of decay has always remained constant. You know the initial conditions, and there's been no contamination. And all the dating methods, you have to make assumptions. Even some of the processes that we point to that indicate a young Earth, these also, we have to make assumptions about the starting conditions, and the rate process, the process being the same as today in the past. Well, clearly, because I believe in the Genesis flood, and geological processes were catastrophic during the flood, and that wouldn't be just sedimentation, it would be other processes as well. And as we found out during the rate project, we had evidence that radioactive decay could well have been accelerated during the flood for a number of reasons. And so, this disparity that we see is based on the assumptions about present rates of decay extrapolated back in time. We found in the rate project, by the way, that the longer the half-life, the greater the acceleration, and also the greater the atomic weight of the parent atom, the greater decay rate. In other words, the slower the decay rate. And so uranium is a very large atom, and it decays, therefore, at a very slow rate. Radiocarbon is a very tiny atom. It has a very short half-life today, whereas uranium has a very long half-life today. So radiocarbon wouldn't have been affected by accelerated nuclear decay during the flood. And radiocarbon, of course, isn't intrinsic to the Earth, except we showed that there is some in diamonds, which are intrinsic to the inside of the Earth. But radiocarbon forms as a consequence of cosmic radiation in the upper atmosphere that circulates then down. The radiocarbon then circulates down into the biosphere, is incorporated in animals that have then, when they die, is incorporated into the fossilized material. So,
Good question here. I heard that at the poles, the cosmic radiation that penetrates, I guess, is up to 4 times as much as, let's say, at the equator. So I know we could assume mixing, I guess, due to winds and other material, but it doesn't all happen. I mean, the prevalence of radiocarbon doesn't occur uniformly across Earth, I understand. Is that right?
No, that's right. In fact, there is a latitudinal difference, and that's well documented in the secular literature, but it's not a huge variation overall that makes for major corrections in the conventional way of radiocarbon dating.
But how much of a difference is it? And another question that comes to mind is, in the decay curve of, let's say, carbon-14, where is it going to be most accurate? Within about the time that it's the first half-life, or, if you're 5-6 half-lives in, does the curve get a lot less accurate, or does it maintain its accuracy throughout the whole curve?
Well, first of all, the variation is only within 5 to 10% between equator and the pole. And so that can be built into the calculation of the radiocarbon dates from the measurements that are taken. But no, the issue is that with the latest technology, accelerator mass spectrometry, you can virtually count radiocarbon atoms. It's very accurate. And so theoretically, you should be able to calculate radiocarbon dates back to 95,000 years. But practically, they found that there was a upper limit of about 70,000 years, which puzzled the conventional scientific community. And so, and it's documented in the literature, they decided, therefore, to test They want to know whether there was contamination in the laboratory, so they went and tested fossil material that they believe should be radiocarbon dead. In other words, everyone knows that after 1 million years, if all the Earth was radiocarbon, there'd be none left. And so anything older than 1 million years should have no radiocarbon in it, period. And so they thought, okay, we'll test coal, we'll test oil, we'll test limestone and things like that, natural gas. And no matter what the age, they always found radiocarbon in it. And rather than conclude, therefore, that the material wasn't millions of years old, they said, well, maybe there are other effects, machine effects or things in the lab that we're not covering for. And so they just make a correction to account for that. But the practical reality is when you go to archaeology, where you can establish certain ages separate from radiocarbon, the archaeologists know that after you go back beyond about 1000 BC, the radiocarbon dates become much larger than the conventional archaeological dates. And so there's lots of problems there with radiocarbon that the conventional scientific community hasn't bridged to the satisfaction of the archaeologists. We're talking about quite a significant deviation in the RATE project. When we looked at 10 coal samples from various coal beds from around the United States, we got samples from the Department of Energy storage facility at Penn State University, where they have samples from every coal deposit around the US stored in the argon atmosphere to preserve it from contamination, and they're available for research. We had 10 samples that varied from 40 million years to 300 million years conventional, and they all gave the same radiocarbon age. And of course, they represent fossil plant material that was all alive at the same time and buried at the same time during the flood. And so that means that material had a conventional age of about 48,500 years, radiocarbon years. So that's an inflated radiocarbon age due to the assumptions not being correct, that if you compare that to a biblical age, the flood being only about 4,500 years ago, then that means you have to recalibrate your radiocarbon ages significantly to align them with the biblical timescale. And so the best way to recalibrate radiocarbon dating is to go to archaeological sites where we can biblically date the site, say from time of Abraham, time of some of the kings, etc., Joshua and some of the kings, etc., and then radiocarbon date those samples and then, establish a recalibration curve. And that kind of research is actually going on at the moment.
Well, if you're able to see individual atoms and count them, I would think that if there's a lot of variability, if there's contamination, you would see a tremendous amount of variability in one object. If you sample from the left side of it, the right side of it, the top to bottom, etc., is that observed?
Well, that's not done. It's not routinely done. You can't. They have to take the sample and digest it and process it. And I don't know of anyone who has done anything significant like that, because it's very costly and time consuming, and no one has really asked those kinds of questions. So I'm not aware of anyone who's done that kind of research conventionally.
But they should, though, because if there's contamination, it's like a microscope. The narrower the field of view you can see, the more areas you have to go to, because there could be extreme variability in a tiny area. So same thing, if you're able to count individual atoms, carbon-14 atoms, the contamination could be a monstrous error signal at that level because you're going so finely grained.
Sure. But the closest that's been done is taking diamond samples and breaking them and then radiocarbon dating the individual pieces. So obviously they're spatially separated samples because they come from different parts of the diamond that was crushed. And generally you don't see variability at all. There's uniformity, but that's diamonds, which are hardest known substance and physically not known to be contaminated and come from inside the Earth. So they're a special case. compared to fossil material. I guess the one way of checking it would be, like, for example, one of the samples I looked at was a fossil tree stump in the coal beds in Newcastle. It had growth rings, and so you could sample individual growth rings to see if there was variability from the core of the tree to the outer part of the tree. Significant trees would be, 50 to 100 years old, and so you might find some variability, but no one's done that at all.
Why has no one done it? I mean, that's kind of crazy. I would think it would be incredibly important to see that, take it. Well,
the conventional scientific community isn't asking questions like that and hasn't done it. And the Unearth creationist community doesn't have access to the technology except through the conventional labs. And we haven't got to that level of sophistication yet because we just don't have the workers and the finances to do those kinds of experiments. But, it's something we could certainly consider doing.
Well, how much do you estimate it would cost to take, some sample 5 sites in it, at various points in the sample?
You've got to get the right sample to start with. We have to be large enough and so you have to do micro subsamples of that material and send them to the lab. I suppose probably $10,000 all up, but it's just no one has gone to the trouble of doing that so far.
Got it.
And also, the other issue is that since we did the work with the RATE project, most radiocarbon laboratories are aware of who are creationists, and we commonly find, for example, we've tried to do more diamond sampling, and radiocarbon labs here and there don't want to know about doing work for us because we're creationists. So that becomes a problem as well. And I mean, I'm not trying to discount doing the experimental work. I'm just saying you've also got to find labs that are willing to do it for you. And
you mean labs refuse? They're like, no, we know who you are. We're not doing it.
Yeah, they don't put it quite as bluntly, although some have. But yes, that happens.
That's crazy.
No, it's the way things are. There are 1 or 2 commercial radiocarbon labs that might do it if they're correctly approached. But yes, it's very difficult.
Well, you said up until I believe 1000 BC that you thought maybe the dates, the speeds of decay were different. Why would that be, and what would have caused that, and how different?
Well, because we know from real-time measurements of the Earth's magnetic field, the magnetic field was stronger in the past, and it's been determined that it has a half-life in its strength and energy of about 1,400 years. So the stronger the magnetic field, the less cosmic ray influx is coming in to produce radiocarbon. So that's going to affect your radiocarbon production in the upper atmosphere. And so that would cause you the problems. And the conventional community, say with archaeological samples for radiocarbon dating, are assuming the influx rate at the present strength of the Earth's magnetic field, the present radiocarbon production. And so you'd have to correct for those effects going back further in time.
Oh, so if there was less radiocarbon production, then it would give an artificially older aged materials at that time. Yes, correct.
Yeah. If you calculate those ages based on the present rate, yes.
How much of a difference would it have been? How much higher was the magnetic field, and how much less radiocarbon would there have been?
Well, remember you double every 1,400 years. So back at the time of Christ, and you can look at some of the pottery, and the paleomagnetism record in the pottery confirms that it was stronger, probably twice as strong back then. And so that's going to significantly reduce your radiocarbon production rate. I haven't done all the sums, but by a factor of a quarter, a half, I guess. And so you're going to affect that the further back you go, and it's going to be significant as soon as you get past 400 BC to 1000 BC. I know got archaeological friends in Israel who are looking at this, and they find radiocarbon at the time of David, 1000 BC, does match the biblical ages. And yet, if you use dendrochronology in some of those wood samples, you find that the radiocarbon starts to diverge in some instances as early as 400 BC, and that's in the conventional literature. So, and of course, dendrochronology has its own set of assumptions. You're assuming one growth ring per year, when if you have fluctuating seasons, I know a research scientist in Australia who's shown that you can get additional rings if you have, wet periods within the 1 year, then you're going to get multiple rings. And that's not always taken into account with dendrochronology. So there's a lot of factors, a lot of assumptions in all of these dating methods. There's a lot of digging into.
I've seen a little bit of an example of what you're talking about. When I was living in New York one year, I think it was February or March, it was a crazy warm spell, and I saw bees and flowers came out for a couple of days.
Yeah, that's right.
Because we're trying to pollinate the flowers. I'm like, wow, this is very unusual. So I could see with a tree, if there was a year where there was a sudden, let's say, warm spell in the middle or the end of winter, maybe a ring would start to be produced, and then maybe the winter reasserted itself, and then the ring, so for that year, you'd see like a very, very thin ring that would appear.
And you've got to take into account the fact that from our modelling of the flood, our flood modelling, with warmer oceans at the end of the flood because of the hot volcanic waters that came out from the fountains of the Great Deep during the flood, that's what's going to generate large storms, that you're going to produce a lot of rainfall in equatorial regions, and in more temperate regions you're going to get higher snowfalls, and so that leads to the post-flood ice age. And so you have evidence of giant lakes in the southwest, for example, and Sahara was fertile with vegetation. Israel, remember in the time of Abraham, Lot looked down on the cities of the plain in the Jordan Valley, and it was well watered, where today it is desert. Central Australia was well watered. And so there's been a lot of climate change, that word climate change, since the flood, which would therefore affect the growth of plants, et cetera, all the way till things started to calm down. 1000 BC, in the time of David, it wasn't as fertile, though he slew a lion and a bear. By the time of Jesus, it's desert. And so, it's very dry. So there's been lots of climate change that affects, growth rates of plants, magnetic field, et cetera, declining rates of volcanic activity since the flood, even slowing plate movements since the flood. And so, all these factors are issues that we've got to do a lot more homework on, a lot more research on, and they have implications for all these dating methods.
Well, also, if you consider, or if one considers fossils, petrified wood, animals that have turned into fossils, I thought a lot of the process was the replacement of the organic tissue by other minerals, I guess per mineralization. So by definition, that's continuing, ongoing, persistent contamination, quote unquote. How could you date such a thing with, let's say, radiocarbon dating?
Oh, well, that's what you have to check. You have to check whether there's any carbon in it. And so coalified material has been permineralized with carbon. It's in place. And so you've got to be sure that your carbon is the original organic carbon. Otherwise, it could well be contamination.
Right, but if the definition of a fossil is largely based by this process of mineralization or other processes such as that, I mean, the contamination isn't even considered contamination. It's just there's a wholesale replacement of the material. So how could you at all date it?
That doesn't always happen. So, for example, you've got the original shells of brachiopods that are preserved in limestones, plant material that's still got the organic tissue. It's not all permineralized. Fossilization is not just simply permineralization. That's where you get replacement of the original organic tissues. And that can happen with silica from hot volcanic waters permeating a cellular structure of the wood, and it silicifies it and becomes, agate, as in the Petrified Forest National Park down in east of Flagstaff. So it's not always, these are the issues you have to check into. Permineralization doesn't always, all fossilization isn't permineralization.
Okay. So some fossils are like that. Some are, I guess, more pristine, but is there a base level of contamination? Except in the case, let's say, of diamond that's underground for a long time. Is there a base level of contamination that you could say affects pretty much all fossils that would be picked up?
No, I think it varies, and you have to be sure of what you're looking at, and that's why, sectioning things and looking at them under the microscope sections, to check what the minerals are, whether you've got the original organic tissue. So you really got to be careful. With fossil shells, it's not so bad because you can readily test them. They're the original material that was in them. Trilobite shells is a mineral chitin, and it's often preserved intact as chitin. And so, you just have to scrutinize what samples you are going to date by whatever method.
Has anyone developed a contamination scale? If you find something that you want to date and it's under these conditions, again, has anyone developed a contamination scale?
No, I don't think so. I haven't seen that.
Is that possible, or would it be useful? Let's say, with your knowledge, would you develop, whether or not it's accepted, but,
I think you'd have to do some homework first before. It's possible, but you have to do your homework first to see whether you can visually detect it and then chemically detect, and then, have a scale of quantity. So it's not an area that anyone has worked in. It's potentially possible. I don't know yet.
Do you think it would be difficult to do? And do you think it would be useful if you had such a thing?
It would be difficult to do, and it could be potentially useful. It would be a yardstick for potentially recalibrating radiocarbon, for example. But at the moment, it's not a high priority for the work that we're doing.
Well, what are some of the priorities in the work you're doing? I should have asked you. I'm sorry. I was just asking my questions. But beyond right now, that's really fascinating to you. We're very important.
Well, been doing a major project in the Grand Canyon where I've been looking at bent rock layers in the Grand Canyon to determine whether folding occurred when the rock layers were still soft or whether it was after they hardened. And the conventional scientific community says, no, the layers in question were deposited 500 million years ago. The folding occurred almost 450 million years later. So the rocks would have been cemented and hardened. And so if you have slow and gradual deformation over millions of years under heat and pressure, the rock become plastic. And so, that's what causes the smooth bending that we see. Whereas we would say, well, wait a minute, if it was soft, it would be more easily bent, posited early in the flood, bent at the end of the flood less than a year while it was still later, it was still wet. Seems to fit the issues better. So no one had actually looked under the microscope to say, well, do you see the effects of ductile processes, that is slow and gradual plastic processes under heat and pressure in the rock? And so that's what I set out to do, and that's what I've been doing. And the results are coming out now is that you can go to the textbooks and say, well, look at document what effects would you see under the microscope, and do we see those effects in these samples from under the microscope? I took samples not just from the folds where they're bent, but also a distance away, and so well away from the folds, and so for comparison, as it were, like a placebo. And what do I find? No difference between no distant difference between samples right in the tight bend in the fold to the limbs of the fold. All the textures, all the minerals are in the same condition under which they were deposited. There's been no subsequent heat and pressure effect. There's been no breakage of the cement, which if it was hardened, it would have hardened soon after deposition in the conventional, within a few millions of years, because all the other layers being stacked on top, and you would affect the cement when you bend it. But no, we don't see any of those effects. So that's been a focus. I've looked at lots of other issues. Radio halo, done work on that, multiple radioisotope dating of various rock units using multiple methods. I did that during the RATE project. Other areas that I've been focused on, apart from radiocarbon, we did helium diffusion work during the RATE project. That was a key component of establishing that there'd been accelerated nuclear decay and therefore faster decay rates during the flood. And so I'm looking at doing further work in that area, looking at other rock samples. We've got other rock samples. We're getting zircons from those, and we're trying to submit those for further helium diffusion experiments to verify the conclusions we came to during the RATE project. And of course, all of this work requires time. It requires funds for experimental work, for field work. And so, that's occupied my time as well.
When you were talking about these folds in the rock, I saw the new movie that, coming out right now, I guess, Mountains After the Flood by the Genesis history people. So I saw some of the folds that you were talking about. It's really weird. You see these rock that looks like sandwiches, the lines in them, again, look like they're folded. Well, they are folded. How did that occur? When you saw those features, what did you think? And how did these get here like this?
Well, it's because the Colorado Plateau was lifted up and it was differential movement at different parts of the plateau, because what happened is that there was fault lines in the brittle Precambrian crystalline rocks that go back before the flood that were reactivated at the end of the flood. And so it's like having two blocks of wood with layers of wet sand deposited on top of them. If you move one block higher than the other, then the sand layers are going to drape over and bend. That's conventionally been done to show that that's what happened. And so, for example, in the Eastern Grand Canyon, there's a 3,000-foot elevation difference. You can go to Desert View Tower and look out to the northeast, and you can actually see north and northeast, and you can actually see where the edge of the plateau, the layers have actually been bent, and then they drop down 3,000 feet out to the area to the east. Then if you go into the canyon where the side canyons are cut through that what we call a monocline, the East Fold monocline, you actually see those folds like the Carbon Canyon fold that was highlighted in the movie. And then further west in the plateau, other blocks moved at different times, and you get monoclines there as well with more folds. So the Monument Fold is an example of that, is mentioned in that movie as well. And so I've doing a series of technical papers to document this. The papers on the carbon, I did one on the Tapete Sandstone, first of all, and then the Tapete Sandstone is bent in the Carbon Canyon Fold and in the Monument Fold. And both of those technical papers have been published this year, and I'm working on subsequent folds right now.
Well, I thought of a joke while you were talking, why you should never marry a seismologist, because they find faults and everything.
Yeah, that's right, exactly.
What did you notice about the, the morphology of the fold? Were you able to sample in the crack of the fold versus on the outer parts? And, what differences did you see?
You don't see anything, some joints. When the rock dries out, it actually contracts and you get what I call joint. And so there's a lot of jointing in the folds. There are some fractures that go between layers, but there's been no major movements along those fractures, except when you go further west in the plateau, there is some active faults there still. Hurricane Fault goes up through St. George, Utah, and there was a 5.3 magnitude earthquake there over 20 years ago, which caused significant damage, and it was movement on that fault. And then I saw the effects of that in one of the other folds in the Grand Canyon, but nothing to the extent that you would predict based on the conventional view. Nothing major, and I've documented all that in these papers.
Okay, so what do the folds then tell you? How do they revise your view of what happened?
Well, they're consistent with the view of what happened, because at the end of the flood, the Pacific Plate was going down under the north margin of the Western North America. Everybody agrees conventionally that's what happened. It was going down. But the convention, they don't understand why it suddenly flattened. Instead of going down at a oblique angle, the plate started to flatten and go horizontally under Western North America. And because this lighter material, called the Farallon plate, was pushed down under Western North America like that, when it slowed down and relaxed, it actually, because it was lighter material, it actually was more buoyant. And so it pushed up Western North America, which pushed up the plateau, which pushed up the Colorado Plateau, which pushed up the Rockies, but also pushed up a lot of central North America, and had effects even over as far as the Ozarks because of that shoving horizontal movement. But from a biblical perspective, we're saying no, plate movement slowed down at the end of the flood. It decelerated, and it decelerated right to the present time where it slowed right down, that it was that deceleration that caused it to flatten out because it was meeting resistance. It didn't have the energy to keep going down at an oblique angle, so it flattened out. And that's what affected the Western North America. And so it doesn't really change my view at all. And so as it was pushing up the plateau, the stresses were different in different parts of the plateau due to the faults that were there from the Precambrian, the crystalline Precambrian basement rocks, the pre-flood rocks, and that affected the softer layers that have been deposited during the flood, and so they got bent where you had this differential movement along the fault.
I've seen in some of the videos that I guess the eruption of Mount St. Helens was a fantastic teaching tool and showing that it doesn't take millions of years for things such as the Grand Canyon to form. In your research, is anyone referring back to or studying the formations, around Mount St. Helens and comparing that to Grand Canyon to further inform what you're doing there? Are there enough analogs that it would help you?
That's been done. For example, Steve Austin has documented that with the pyroclastic flow. When you have very fast movement of water and a mixture of grain, you will get multiple graded bed. And that was what was observed in a 3-hour event. In a 3-hour event, eruptive event, three-way speed pyroclastic flows with mixture of steam and volcanic ash settle out to produce some 25 feet of these alternating layers of different grain sizes that are consistent totally with and comparable to what we see in some of the layers in the geologic record, some in the Grand Canyon. And so, and then flume experiment to show the same thing with mud rock. Mud rocks, if the water flow is fast, the mud particles flocculate to produce sand-sized particles that then settle at the rate and transport and settle at the rate at which sand particles settle. And we know that can be very, very rapid. There has work being done to compare what we saw at Mount St. Helens with what we see in layers in the Grand Canyon. Steve Austin has done a lot of that work, and he continues to do some of that work too.
What are some important analog that are observed between the two? And that's a general question.
Yeah, well, the rapid formation of multiple layers that I just discussed, and then the carving of a 1/40th scale model of the version of the Grand Canyon in the North Fork of the Toutle River, in less than 24 hours. I mean, they're the two major analogs that people draw from Mount St. Helens. To go further, you have to, with different types of rock, you have to go to flume experiments and those sorts of things, and field observation in the present world of water transport, say when hurricanes deposit sand when they sweep inland on the east coast of the US, or sand waves in Long Island Sound, for example, that simulate crossbeds that we see in the sandstone layers in the Grand Canyon. So there's a number of analogues that we can, in the present world, as a window into understanding some of the features we see in layers in the Grand Canyon and elsewhere.
So the Grand Canyon, do you have a picture now of how it's formed and how fast it formed, and that's different from the conventional picture?
Oh, yes, we do. And it's illustrated in that documentary that's just coming out, that when the plateau was pushed up, say the East Kaibab monocline, Kaibab Plateau, I said there was a 3,000-foot elevation difference. That meant that water would accumulate in these lower areas to produce lake systems. And there's evidence that there were lakes east of the plateau, east of where we got the Grand Canyon now, and also up in what is now the headwaters of the Colorado River. In fact, Bryce Canyon is not a canyon per se. It's actually eroded features at the edge of a plateau. And it's been shown that those features were eroded as a consequence of a lake that was peripheral to the plateau, and rapid drawdown in soft sediments would produce the features that we see in the edge of that plateau. That's one of the lakes that Steve Austin and others have modeled, that with continuing rainfall after the flood would get to the point where they would breach the obstructing wall that was holding back the water. And so you'd have spillover erosion. And in that movie, he shows with a simulation, one lake fails upstream and it spills into the next lake, which causes it to overtop. And a whole sequence of lake would carve out the canyon very rapidly. And it's quite obvious, because when you look at the canyon, as we often show people when we start the river trip, we go to a vantage point where you can look downstream, and you immediately notice that two things as you traverse through the canyon. First of all, the walls of the canyon don't have millions of years of debris that's accumulated from collapsing from the cliffs. And secondly, the rapid have been produced by flash floods in the side stream. And the Colorado River, even pre-dam, whatever flood level you want to envisage, the present rate of flow is often fluctuates based on water releases of between 8,000 to, I was in the canyon and they had a 40,000 cubic feet per second release. But historical floods have been known to be up before dams 100,000, 200,000 cubic feet per second. But none of those are capable of cleaning up the channel, removing the debris that's been brought in by the flash floods. The rapids have actually grown. New rapids have formed from more flash floods. So the Colorado River isn't capable of cleaning out its channel today. So how could it have carved out the Grand Canyon? And whereas if you have a rapid drawdown as a result of spillover erosion, a lot of water, a little bit of time, it would take all its debris out with it. And so if that was only recent, then the present debris that we see at the base of the cliffs is only what's accumulated in the thousands of years since the dam burst carved out the Grand Canyon. And so we do have a very viable model. And interestingly, back in 2020, there was a group of conventional scientists who don't believe in Noah's flood, who have similarly proposed, and they did a simulation in a large flume tank of a similar lake spillover dam burst model for the canyon, and did produce a similar scale in their simulation, a model of a resulting canyon that matches the Grand Canyon. And they're not believers in the flood, and yet they believe in a catastrophic erosion of the Grand Canyon.
Okay.
Yeah, if you want the documentation of that, Steve Austin produced with two others a paper that we published in our Answers Research Journal that's available online, open access. You can download all the PDFs, like my technical papers on the folds in the Grand Canyon. And he documents in the reference list, you can see that Douglas et al. Back in 2020 did that simulation. And I think it was six authors, and it was published in a Journal of Geomorphology or something like that. I forget what the title it was, but you can check that out. It's all available online.
So what time scale would have the Grand Canyon formed in, you believe? What was possible or likely?
Well, within decades or a few centuries, you'd build up the lakes because of these high-volume storms that I mentioned earlier, because of the warm oceans at the end of the flood. And the canyon would have formed, therefore, in a matter of weeks to months with these dam breaks catastrophically eroding through the plateau. And within centuries after the flood, that means the layers would have had time to dry out and be cemented and hardened. And so remember, I'll come back to them. So that's why the walls would have stood up. If the rock layers were still soft, there's some that say, oh, no, it was done as a consequence of the flood. No, the very fact that the cliff stood up meant that there had to be time for the layers to become cemented. And so that would be the drying out after the flood. And so an analogue, by the way, is the erosion of the channel scabland in the Pacific Northwest. J. Harlan Bretz, back in the 1910s, 1920s, proposed, and he was totally not opposed by the conventional community, but he proposed that an ice dam burst there was a glacial lake called Lake Missoula, and the ice and debris from the retreat of the glaciers had dammed up these waters, and a glacial outburst dam of breakage carved out the channel scablands in a matter of a day through solid basalt. And it wasn't until the 1950s, that he was actually recognised for his work, and the conventional scientific community came on board. So now if you went into we got the Penrose Medal from the Geological Society of America for his work, pioneering work. And so there is an analogue that's recognised in the conventional community that if you have a lot of water and a little bit of time, it can cut through solid rock to produce large canyon.
Amazing. Well, very good, Andrew. Where is the best place for people to start learning about the ideas you've been working with, and to see some of your lectures? Where could they start from?
Well, go to the Answers in Genesis website, and you'll see some of my lectures there, and my book, Earth's Catastrophic Past, which has been republished as Revisiting the Genesis Flood. They're available online. You can see where they are. My lectures are available online, my articles, and that will include all the articles that I did for the Answers Research Journal. You can scroll down on the AIG website to the Answers Research Journal, and you can search for papers there on the Grand Canyon, the carving of the Grand Canyon, Steve Austin, work on the Coconino Sandstone in the Grand Canyon by my colleague and friend John Whitmore at Cedarville University, showing that they were deposited during flood. The layers, the Tapeat Sandstone that I referred to earlier that's been bent, the layered paper on it to show it was catastrophically formed during the flood. So there's a wealth of material that is available online, free of charge.
Okay, excellent. Well, Andrew, thank you so much for coming on the podcast. I appreciate it.
Thank you, Richard. All the best to you.
Thank you for listening to the Good Question Podcast. Please email support@thegoodquestionpodcast.com if you have any referrals to great guests for us to interview. Visit thegoodquestionpodcast.com to hear more interviews. And please help us spread the word by rating and reviewing us on Apple Podcasts, iTunes, Spotify, YouTube, or wherever you listen to this podcast.